This work presents a new method for reachability analysis of general systems using random set theory and adversarial sampling. Reachability analysis has many applications in robotics. For instance, consider a robot hopping on an asteroid in space, and in this case, the gravity field of the asteroid is highly uncertain. And to guarantee safety of the system, one must guarantee that the reachable set of states of the robot does not intersect with a crater, for instance, so that the mission can be successful. Reachability analysis has many other applications. In machine learning, for instance, one can use it to do verification of neural networks. So in general, the problem can be stated as follows. We have a dynamical system with dynamics f. Its state is parameterized by x. It's controlled with controls u. It has uncertain parameters theta, for instance, the mass of a drone, and subject to external disturbances, for example, wind. And so we assume that all uncertainties are inside compact sets. And the question is, how do we compute the reachable set of states where the robot is guaranteed to lie at all times in the future? In this work, we make extremely few assumptions. Namely, we only assume that the dynamics f are continuously differentiable and that all uncertainties are bounded. And with this approach, we are looking for a method that is efficient, that is accurate, that scales well with the uncertainties, with the dimensions of the uncertainties, and works even if the uncertainty sets are updated. For instance, in learning-based control, one may observe data from the system and refine the estimates of the mass of the drone, for example. So imagine computing these reachable sets exactly. Well, they are the image through the dynamics f of the initial set for all possible uncertainties. So if we could evaluate f at all points inside these sets, we would have the true reachable set. But in general, this is computationally intractable. So instead, what if we just take a few points inside these sets and we propagate them through the dynamics f, and we end up with points which are guaranteed to be inside the reachable sets? So now we have points inside the reachable sets. The question is, how do we estimate the reachable set from this finite number of samples? So what we propose in this work is very simple, is just to take the convex hull around these points. So now we want to understand what is this set. Well, if we run the algorithm multiple times, we'll get different convex hull, different sets. So one must say these sets are random because they change depending on the sampling. So we can mathematically describe them using random set theory. And why do we care about mathematically describing them? Well, because we can, using random set theory, prove that as we get more points, these convex hull converge to the convex hull of the true reachable sets asymptotically. So this motivated this randomized uncertainty propagation algorithm, and to the best of our knowledge, is the first use of random set theory in robotics. Now comes the idea number 2 of this paper. We see that the accuracy depends on where the samples lie. For instance, if we get more points that are inside the convex hull won't change. And so instead, if we get a few points that are outside the convex hull, the approximation will get much better. And so from this, we designed an adversarial sampling method, which is inspired by literature on robust training of neural networks and leads to improvements in accuracy and efficiency. So in the results, we show that it outperforms prior work, and we show that the method is fast enough to be used for trajectory optimization and control of highly uncertain systems. So in conclusion, we propose 2 very simple and efficient approaches for reachability analysis of general systems. So the method can be used straight away for general systems with high uncertainties for which there are no alternatives available in the literature. We proposed a new interpretation using random set theory, which probably will have other applications in robotics. And we also show that the method can be used with Bayesian neural networks where the weights are updated over time and used for learning-based control. Thank you. I'm happy to take any questions.